And without further ado, on my left, on your right, is our next speaker. His name is Jim Barton, and he's a field engineer for Solo.io, right? Whose enterprise software career spans 30 years. He has enjoyed roles as a project engineer, sales and consulting engineer, product development manager, and executive leader of tech startups. Prior to Solo, he spent a decade architecting, building, and operating systems based on enterprise open source technologies and the likes of Red Hat, Amazon, and Zappos. After 2 years of COVID-driven Zoom-encrusted isolation, I like that one, Jim especially enjoys sharing with and learning from three-dimensional people at technical conferences around the world, such as here, I believe, right here. The title of his talk is The Future of Service Mesh, Sidecars, Sidecarless, or Both. Please give a big round of applause, Mr. Jim Barton.
Thank you. All right, welcome everyone. As I really do enjoy leading these discussions with three-dimensional people, so it's very good to have you all here in the room. Let me just check on one. Pay no attention to, okay, everything is good. All right, very good. So, good day. Today we are going to talk about service mesh technology and the future of it. We're specifically going to focus on some of the significant architectural changes that are currently in flight within the open source Istio community. How many Istio users are there in the audience today? Istio, okay, very good. Other service mesh technologies potentially? No? All Istio, okay. Oh no, I saw one hand back there. Very good. Glad to have you all here. So my name is Jim Barton. I am a field engineer with Solo in North America, and you've already heard my intro, so I will skip that. So who is Solo? Solo is a company that was born in the cloud that helps enterprises manage the complexities of cloud-native application networking. We do that through leadership in a number of open source projects, most notably for today's talk, the open source Istio service mesh, also things like Envoy proxy and GraphQL, and of course we offer products and services based on those products. Okay, so I want to set the stage for this discussion with a story that takes us back to an event that occurred just before this photo was taken in my senior year of engineering school. So that was over 3 decades ago, and as you can see, if you look carefully, I had a lot more hair in those days, so you'll see what a lengthy career in enterprise software computing will do to you if you're not careful. So let me actually kick off a video here to give you some context. There's no sound with this, but you'll get the idea of what I'm going to talk about. Oh. There should have been no sound with this. There we go. There's the no sound. Okay, so this story arises from a competition that happened with my university's IEEE chapter, where we competed against other schools from around our region. So it was an autonomous robot car racing tournament that looked very much like this video, only we went a little slower in those days. This was many years ago. And so each car had to trace this thin black line around the track, and the winner of each dual heat was the one that completed the track the most quickly without, of course, running off the course. So I want to tell you, this was a lot of college students. It was a very high-energy competition. There were entries from several engineering schools in our area, and they had some very interesting designs. Some of them were pretty complex. Some of them were a little bit funny. But there were 2 notable vehicles that worked their way through this single elimination tournament bracket. One of them was this huge behemoth of a design. It had this giant cylindrical core that was surrounded by this 3-legged metallic superstructure that was chock full of D-cell batteries to give the thing enough power to run, and the superstructure would rotate as it navigated its way around the course. And so this entry came from a very large, very well-respected engineering school that brought this massive student delegation with it, and they cheered their entry all the way through to the finals of this tournament. But then there was this other entry that worked its way through the opposite side of the tournament bracket. And from a design standpoint, it was the polar opposite of this giant behemoth design. It was a tiny little device from a small engineering school that had only sent one delegate to this particular conference. He used what appeared to be the chassis of a child's slot car, and he had added a little photo detector at the front that would sort of sweep along as it was going down the track there. And it was driven by this small motor and powered by a single AA battery that was wired into the chassis. And surprisingly, it started beating its much larger, much more well-funded competition. So after an hour or so, we reached the tournament finals, and there were two vehicles left standing. The massive behemoth with the rotating legs and the giant cheering section versus the tiny single designer slot car. So who won the coveted championship trophy in the tournament finals? Come talk to me after the end of the talk and I'll let you know. No, just hang on till the end of the talk and I will let you know who won the competition. So let's talk about this. So I learned a lot of things in my senior year of engineering school. I've honestly forgotten most of the specifics, but this particular event seared into my consciousness a lesson that has served me well over the intervening 3 decades, and that is the lesson of parsimony. Parsimony is the law of simplicity. When you have a design goal in engineering and there are multiple paths to reach that goal, all else being equal, generally speaking, the simplest path, the fewest moving parts, represents the best option. In short, simplicity trumps complexity. So as we transition into talking about the future of service mesh technology, here's the way I see this marketplace trending right now. It's all about simplifying. Simplifying architectures, simplifying adoption, simplifying operations. There have been some really exciting developments along those lines over the past few months, and we're going to explore those in this talk together. But first, because a lot of you don't have a ton of service mesh experience, I want to go back to the beginning and lay some more groundwork here. So let's say you're living in prehistoric times, circa 2017, let's say. And you are perhaps in a financial institution or a government agency, or maybe you're a part of some enterprise that's in a heavily regulated industry like telecommunications. And so you have these two services that need to communicate with one another, Service A and Service B, let's call them. And in that prehistoric time, before the dawn of modern service meshes, you have a regulatory requirement that communication between all of your services, even your internal ones, all of that communication has to be encrypted using mTLS for security purposes. So how would you satisfy that requirement in this prehistoric time? Well, perhaps you'd Google, TLS libraries for the languages or frameworks that you're using, and you'd integrate those with your application stacks, and then you'd test it and deploy it and mark the requirement as satisfied. And that approach is fine as far as it goes, but the people in this room, we don't live in such a simple environment like that, do we? In fact, many of us operate in a service ecosystem that looks something more like this. I spent a number of years at Amazon, and one of the posters in our office depicted what we affectionately call the Death Star. And the Death Star represented a snapshot at some point in time of all of the services in the internal Amazon application network and how they all interconnected with one another. So the simple approach we envisioned on the previous slide of individual services building out their own unique solutions for security and observability and connectivity, right, they just don't scale to Death Star size, do they? So these challenges caused our community to ask a number of important questions about how we could achieve vast microservice networks at scale. Questions like, how do we secure service-to-service communication? How do we manage timeouts and communication failures? How do we control traffic? How do we publish metrics so we can see what's going on among all these services? And perhaps in some ways most importantly, how do we accomplish all of this in a way that's simple and repeatable and embraces important principles like infrastructure as code and declarative configuration? So we realized as a community that a lot of these concerns were cross-cutting, that they applied to all of our services within our networks, true? So rather than taking on all this undifferentiated heavy lifting within each application, wouldn't it be better if we could externalize those capabilities and handle these cross-cutting concerns in some kind of outside component? And so one of the first data plane architectures that emerged from that era in practically all service mesh platforms uses a technique called sidecar injection, and you see that depicted on the after side of this slide. So, a sidecar container that lives next to the application workload handles all of these cross-cutting, connect, secure, observe concerns on behalf of its associated service. So that allows us to remove a lot of undifferentiated heavy lifting from our application teams. And so capabilities like the ones that are enumerated on this slide could be handled more effectively within the service mesh infrastructure. We won't walk through all the details here, but as you can see, the key pillars are connect, secure, and observe. So where the service mesh community landed from an architectural standpoint, and this is true whether we're talking about Istio or one of the service mesh alternatives that's out there, is that we have an architecture with two components, a data plane and a control plane. So the data plane is responsible for the request processing and routing. What happens is that an Envoy proxy would be injected into the service pods as a sidecar. And this sidecar is responsible for all those cross-cutting, connect, secure, observe capabilities on behalf of the application service. So when service A needs to talk to service B, the Envoy sidecars intercept all of the inter-service communication, and they manage things like securing the communication channel, managing request timeouts, failure policies, publishing metrics, and so on. So it removes those burdens from our application teams. And so if you have a mandate for something like securing inter-service communication across a large application network, then by injecting these sidecars and supplying some pretty simple declarative policies, you can achieve that objective within your mesh without requiring any modification to the underlying application workloads. And that's a big deal, and that's the data point. Well, the data plane can do nothing without a control plane to specify the policies to tell it what to do. So the control plane is the brains of the operation. And when outside stimuli are applied to the mesh, let's say a new service failover policy is being applied, then the control plane is responsible for ingesting that new policy, translating that into configuration for the applicable Envoy sidecars, and then pushing that configuration out to those sidecars throughout the mesh. And at a high level, that's been the general state of service mesh architecture for some time now. And let's be clear here, there are many enterprises who have been and are now successful in utilizing this architecture. And it does solve a lot of problems in managing complex microservice networks without requiring changes to underlying service code. But let's be honest, there are also operational challenges that have emerged as we've gained experience with service meshes and with this model. So we've learned a lot since Istio 1.0 went GA back in 2018. There's this great quote from a senior engineer recently of T-Mobile named Joe Searcy. He spearheaded much of their early service mesh adoption, and he says this: the biggest enemy of service mesh adoption has always been complexity. The resource and operational overhead to manage the service mesh for a large enterprise makes adoption cumbersome, even as projects like Istio have worked to decrease that complexity. So, while Istio does what it does very well, there are opportunities to simplify its operation and lower its overall cost of ownership. So we're going to explore very quickly some of the dimensions of that complexity that the community is seeking to simplify, and we'll follow that by delving into some of the emerging innovations in the community that address those challenges. Okay, so first of all, we're going to take a look at operational complexity. So this diagram depicts a typical Istio deployment, obviously reduced to a much smaller scale than usual. You can see we have 3 nodes that are deployed in this case, in our Kubernetes cluster. There are a number of apps deployed, some of them with multiple instances deployed, perhaps for enhanced availability or performance. And because we're using Istio, we have an Envoy proxy sidecar that's injected into each one of those application pods. You can see that depicted there with the little pink, the pink hexagon. So let's consider some of the operational issues that could arise here. Let's say you're applying an update to a service, or perhaps you need to upgrade to a newer version of the Envoy proxy itself. And when you recycle these services, you might encounter some kind of a race condition where the service container spins up more quickly than its associated sidecar. Then as the application begins to operate and perhaps issues some requests to other services, those service requests might fail because the sidecar that's responsible for intercepting and routing those requests isn't yet available. So you potentially suffer failures. Perhaps the service can't even initialize itself properly. And there's a mirror image set of problems that occur when a service needs to shut down. So you can design around these sorts of issues, but remember, our goal with service mesh is to simplify the life of the application services, to separate those effectively, not to make it more complicated. So we'd like to simplify some of these operational complexity issues. All right. Another challenge with traditional mesh architecture arises from the fact that we want the mesh to be as transparent as possible to its resident applications. But the reality doesn't always match that objective. For example, our diagram here depicts a case where we have a Kubernetes pod that contains something called job 1, and that job needs to run for some period of time, complete its mission, and then shut down. So the operational problem we encounter is that when jobs like this shut down, sometimes the injected sidecar is still running, and that can prevent the environment from cleaning up after itself properly and recycling those resources in a timely fashion. So we'd like to clean some of that up as well. Also, there is the popular topic of latency. So in a traditional architecture, there are Envoy proxies that are injected into each application workload, and these are full Envoy proxies with a full layer 7 TCP stack that has to be traversed with each request and response that goes in and out of a service. So there are latencies that accumulate as you traverse the proxy network for a large scale service network. And these can add up to a few milliseconds of extra processing time. And when you multiply that by a service network operating at scale, it can add up to a noticeable operational impact. So we'd like to make some improvements in that area as well. And finally, one that's on everyone's mind, let's consider the cost components of traditional service mesh architecture. So all these Envoy proxies that we are provisioning to run alongside our workloads, they consume CPU and memory, and they cost money. One of the phenomena that we see at Solo in our business is that enterprises tend to over-provision these sidecars. And the reason why is pretty clear. If you under-resource your sidecars, then that can have a very negative impact on the application workloads that they are serving. So we frequently see people put excess capacity out there, and that can have a negative cost impact. So we'd like to make some changes that shave cost from our service meshes as well. So these are some of the challenges we see as enterprises adopt and operate service meshes. And so while the model has worked pretty well for a few years, as a community, an open source community, we'd like to learn from user experience and address some of these challenges that we've outlined here. So engineers from Google and from Solo.io have been working on these problems for well over a year now. We actually discovered separately that we were working on them independently and then joined forces to collaborate. So back in September of last year, we jointly contributed to the community a new sidecar-less data plane option for Istio called Istio Ambient Mesh. It's been available since Istio 1.15 as an experimental profile, and as of February, it now lives on the main branch of the project. So while the community isn't recommending it for production use just yet, we expect that to change over the course of this year. So there's been this large wave of interest in the community, and Solo in particular has been moving aggressively to deliver education around ambient mesh as well as to integrate it and make it enterprise ready. So we anticipate a number of important benefits that are flowing to users in the service mesh community based on ambient mesh, and those include some of the things we were talking about before, things like cost of ownership and simplifying operations and reducing cost. And let's just briefly explore those here over the next couple of minutes, and hopefully with time for a little demonstration as well. So one characteristic you note right away is that it's much easier to get started with Istio in ambient mode. So when you're working in the traditional architecture, every workload participating in the mesh has to be injected with its own sidecar proxy, and that can be a pretty heavyweight process at scale. So by contrast, the ambient onboarding process simply labels namespaces to indicate that ambient is the desired operational model. So basically all of the workloads and the relevant infrastructure can spin up without any changes to the application service pods. Okay, So if we turn our attention to how ambient's going to work, there are really two different sets of components that come to play here. So we're replacing the sidecar-based Envoy proxies with a different model where the routing and connection and observability capabilities are extracted into separate components. And there are really two layers that are at work here in the ambient mode. So first is a secure transport layer that operates on a per node basis, and it handles just the lower level layer 4 networking issues. So its primary purpose is to manage securing communication traffic between workloads. Then where you need to apply policies that include concerns like routing based on HTTP headers, maybe retries or fault injections, anything that requires access to the higher levels of the HTTP stack, the environments of those policies will be delegated to a separate set of Envoy proxies called waypoint proxies. So there are two layers to this new data plane architecture. The first is the ztunnel, the zero trust tunnel, that operates on a per node basis and is responsible for layer 4 mTLS security concerns. The second is the waypoint proxy that operates on a per service account or per identity basis and is responsible for higher level L7 concerns that are typically associated with HTTP. But the Istio control plane architecture is still based on Istio D that you see depicted at the bottom of the diagram there. That basically remains unchanged. So it's going to respond to the same APIs as before, only now, in addition to knowing how to program sidecar proxies, it also now knows how to program these new ztunnel and waypoint proxies. Okay, so there are two new layers of the ambient mesh architecture. Let's assume we just care about the security capabilities of Istio, and that's a common adoption pattern that we see in enterprises at Solo, where a new user of Istio doesn't necessarily want to bite off on the entire service mesh infrastructure, but simply wants to, say, be able to secure traffic between their services, such as a financial institution, perhaps a government agency, something like that. And so in that case, for example, government agencies, I know in the U.S. and perhaps here as well, have mandates where they are required to adopt zero trust architectures, where all of the traffic moving internally between services has to be encrypted and secured with mTLS. And so satisfying that mandate is job one. The other benefits of service mesh really are not as necessary for them in an initial adoption model. And so basically what happens is in a simplified model, the only thing that's required here are these ztunnel components that live on each node. So app A wants to send a request to app B. There are no sidecars in play here. App A's request is directed to its local ztunnel, which then establishes a secure connection with ztunnel on the target machine, and then the request is forwarded from there to the workload and back along the same path. So if security is the primary use case, then you can get by with kind of incrementally adopting just these components of Istio that you need without requiring the addition of sidecars or even the new waypoint proxy. So incremental adoption is a really nice benefit here. Now, in cases where layer 7 processing is needed, and a lot of times they are, you want to do things like fault injection, you want to do routing based on higher level HTTP components, then we introduce this waypoint component. So these proxies are established on a per namespace or per service account basis, and they can be deployed wherever you want using standard Istio deployment, standard Kubernetes deployment techniques. So you can manage them using these standard techniques, and you can scale and distribute and manage replication of them just as you would with any Kubernetes component. So, but again, from a policy standpoint, nothing really changes. You use Istio APIs to declare the layer 7 policies that you want, and the Istio control plane manages the distribution of those policies to the appropriate enforcement points. So we have these two layers. There is the per node ztunnel, the per identity waypoint proxy, and right out of the gate you can sense the reduced cost in this approach. So instead of having all of these injected sidecars, now you have a much simpler model where basically those policies are collapsed into, or sorry, those sidecar components a single ztunnel on the node. So there's a lot of opportunities for cost reduction there. And based on our preliminary analysis at Solo, we've seen some pretty dramatic reductions in the cost with people who are thinking about ambient. There's some blog information there if you'd like to drill on that more deeply. So in addition to cost reduction, there's also a ton of benefit that comes from simplifying operations. So we've discussed some of the issues around onboarding and offboarding applications in the mesh, and also around upgrading applications or infrastructure in the mesh. This becomes a much simpler process now, especially at scale. For example, let's say there's an Envoy CVE patch that you require that needs to be applied, and we need to apply a rolling upgrade of that patch throughout our application mesh. Well, we no longer have to schedule downtime and recycle every single workload in order to make that happen. With Ambient Mesh, we can simply update the L7 waypoint proxies, and then changes will be effective immediately throughout our service mesh without a lot of downtime, and that represents a really big benefit. So if you think about what's happening here graphically, we're actually moving from an environment like this with a proxy injected in every workload to something like this, where at layer 4 we just have a single deployment per node. And then where we need layer 7 policies, we can spin up separately waypoint proxies to manage that. So it's a much simpler operation. So from a performance standpoint, let's take a look at basically it's a real simple analysis of the latency here. There's actually more details about this on the Solo blog as well. But the idea is, rather than traversing the full layer 7 sidecar proxy stack on each request 2 times at the source and the destination, now we can cut that down quite a bit. In some cases where we're not even applying layer 7 policies, we only have to traverse the ztunnels, which are much lighter weight layer 4 entities only, and so it's much faster in terms of processing time. And even with layer 7 requests that require layer 7 policies, we still see some incremental improvement there, which is a really good thing. Okay. Unfortunately, I don't think we're going to have time for the demo here, but don't worry, because if you're interested in seeing this in action, I want to invite you to come back tomorrow. I believe at 3, it's in the afternoon, 3:30 or 15:30, 15:40, something like that. And we're going to run through a workshop where we actually, if you bring your laptop with you, we will all work through an exercise together with a slightly more relaxed time frame where you can see Istio Ambient Mesh in action. So if you're interested in that, I would definitely encourage you to come back and to see that demo. Okay, so but basically just summarizing where we've come here is these 3 core benefits are the ones that really stand here, and they really represent the maturity I think of the Istio open source project and the community in making this something that's ready for production use, even within large enterprises. So really simplifying the operations, which we see as job 1, reducing costs, and also improving runtime performance. Okay. So in terms of responses to Ambient Mesh that have been out there in the community, we've seen a lot of really enthusiastic support. We've seen a few wait-and-see responses as well, but this is probably my favorite one. This is from Matt Klein. If you don't know who Matt is, Matt's an engineer at Lyft who created the Envoy proxy. That's actually the foundation for Istio and a lot of open source or a lot of API gateways that are out there these days. And he basically says this is the right path forward. Sidecars have always been an unfortunate implementation detail. Many features can now move into the underlying infrastructure, and is excited to see how this evolves. So that's a pretty solid endorsement there. Also, our friend from the earlier slide, Joe Searcy, had this to say: basically, the opportunities that Ambient Mesh provides are very exciting, and again cites a lot of the things we've talked about earlier in this talk: better transparency, fewer moving parts, simpler invocation, and big potential for savings in resources are really good things. One other response I'll highlight here is that this has also led to basically the community continuing to grow. So this is from an announcement that came out just 2 weeks ago, where if you're familiar with the service mesh ecosystem, Microsoft has had a service mesh that it sponsored on its own called Open Service Mesh, Envoy-based, very similar architecture, and they recognize with the kind of the size and the level of innovation that's coming out of the Istio community, that they wanted to be a part of that. And I can tell you, I know some of the engineers at Microsoft personally who are working on this, very, very, very bright people. And so what they've done is basically Microsoft has announced, we're going to retire our existing service mesh project, and we're going to devote our resources to the Istio project, which is a really good thing. Okay, I have about 3 minutes left here, and I really would like to be able to take some questions. So, if it makes sense, if we have anything on the chart there, or you can you got one, all right. It's
Let's give Jim a big round of applause. Thank you. We have a few questions for you coming up on Slido, but I also have this handheld microphone in case anyone has a question from the crowd they would like to ask Jim. Any takers? Old school style. Okay, all right.
no old school.
While we're waiting to get the Slido up, I'd like to present you with your gift.
Well, thank you.
So we have a Budapest notebook, and I've been instructed to hold this picture up for the camera, which is not a picture that I've drawn of Jim, but it is a beautiful picture of you.
That's impressive.
Yes, so this for you.
All right.
Here you are, sir.
Thank you, Alex. I appreciate that.
Thank you. So just another minute here before we get our Slido questions up, but I think I've given you enough time to think of a question. So would anyone like to save the day, be my hero, and ask there, we have one right here. Can I get the handheld mic, please? Can you please say your name?
Hi, my name is Andor Polgari. I have one question. Who won the competition?
Okay, the question is, who is the competition? I think, I mean, this is an open source project, right? So I don't think we see competition in the traditional sense. There are alternative service mesh technologies out there.
Not that one. The racing competition.
How did I forget? Yeah. Yep. So basically, the racing. That's great. That's the one thing you're all going to remember from this talk, right? We get down to the finals of the event. There are two entries left standing. There's the one from the big engineering school with the giant design and the cheering section, and there's the one with the single guy in the little tiny slot car. And so basically, the little tiny slot car, everyone knew it was faster. And so the engineers, they have the engineers for the larger entry, they have two guys who carry it up to the start line, and they're screwing up all the potentiometers to make it go as fast as possible. And so the race starts, and they take off down the track, and as soon as they hit the first curve, because they've screwed up the potentiometer so much, the thing goes off the course and is disqualified. And so at this point, the little entry was by far the crowd favorite, and so everyone just burst into cheers. And so the little guy won the competition. So thank you very much for asking that.
Wonderful, thank you. Jim, we have time for one question. Could you pick one that sounds the most interesting to you?
Oh, wow. How mTLS, are there any production deployments of ambient mesh? Well, this one's a quick one to answer. Are there any production deployments of ambient mesh? The answer is no right now. This is still in preview mode. It will be in production by the end of 2023. We at Solo and a lot of other people are working, the community, it's top priority for the community to get this into shape where it can be done in production. So, yeah, absolutely.
All right. Thanks so much. Jim, are you in town today and tomorrow?
I am. I'll be in town tomorrow. We'll be presenting at 3:30, I believe, tomorrow for a full, in a little more relaxed time frame where we can go through this actually hands-on.
Wonderful.
Yep.
One more time for Jim Barton, everybody.
All right. Thank you all.